that's fine with me. And we'll get going. So um, this is briefly about me, mostly to say I work at Redgate Software. Been there for 2 years this week and been doing the database thing in other platforms over the years for about 22, 23 years. So it's been great to be a part of Redgate and help them, understand the Postgres community more and provide value and just help to the community. So that's one of the reasons I really love being here. I'm available at Ryan Booz just about anywhere. Feel free to reach out. Um, this is, I'm going to skip a few things. So I've given this talk a few times. I'll be in Athens if you happen to be there. Um, and there are a couple recordings and I've some updated content. I'll probably make another recording soon, but I want to get to the basics of what and why. Like why would you want to use partitioning? And, then briefly what the types of partitioning are that we support within Postgres. Quick overview of how to actually do the work, how to create it. I may or may not do the demo. It's not long, but you guys can decide if we have time and you want to. And then just a couple tips or recommendations right now, particularly based on some updates recently in Postgres. So pretty quick. Let me know if you have questions. We'll keep going. So the what and the why. I use this picture for a lot of things because I just love this picture for some reason of how disorganized life can be. And the reality is our data is often more disorganized than we think or we know. And so as your data grows, if it's just kind of spread out everywhere, and the reality is in a heap-based architecture, we don't really have any control over where data resides next to other data. And so you could have a row for one date and timestamp, that is on one page and one that's on another page that was created a long time after that, a long time before. So, the indexes help you get to that data, but where data is located and kind of how easy it is to access similar data together without having to pull lots of random pages is tricky if you don't have some other way to do this. So you can have lots of data. You might know how to get to the thing you want in this stack of mess, but it might be all over the place. And it's not easy to go to one spot and get lots of the same data. And so, if we think of partitioning as something along the lines of this, it doesn't mean that all of the data pages on disk are actually stored next to each other in a neat little box, but it means that all the data within the pages that are together are a part of that partition and part of the way that we're segregating our data. So at least it's a little bit easier to identify this is where I want to go to get the data. It has, some other characteristics to it that make partitioning really beneficial for large data sets. Think of partitioning also as just a way to really define the boundaries of your large data. So if you're old enough to ever remember going into a library and seeing a card catalog, you know that whatever's on the front of the label, everything in that drawer is going to match up with that range of text or whatever that might be. And then the other thing that partitioning does for us is actually can provide, multiple ways, multiple paths to get data in, depending on how you're loading data, depending on how you're partitioned. There's a lot of ways that, you won't step on other processes sometimes. And so you can get fast load of data and even fast access if one query is going one place, one query is going another, and that data is residing in shared buffers more regularly because of how you're working on it. So throughput can absolutely be a benefit depending on the kind of data and how you're partitioning it. And really, it comes around to one or two people have been said in the intro. It comes around to, large tables over time don't scale terribly well, uh, particularly for a lot of the usage patterns that we tend to have when we want data that's recent, time-based data in particular. Often we're querying stuff that's more recent, more frequently, but then we have to go get older data sometimes. And so really partitioning is about trying to help solve that problem, both in performance and just in overall maintenance of how we deal with data. And so what does that really mean? So partitions are honestly just regular tables. So we have a table that we say, I want this table to be partitioned in some way. And then that just is a shell on top of within declarative partitioning. It's a shell across all the other tables underneath, but the tables, quote unquote, underneath are just regular tables. They have schema, they have a table space, they have, they are in many ways function just like a regular table with a couple of caveats. So these children tables they are in documentation, the partitioned table is the parent, and the partitions are the the smaller children, the actual tables that are storing the data. And so, because they are actual tables, they have everything about a table. Self-contained indexes is one of the big advantages. And then, because they're tables, they themselves can also be partitioned if there's a use case for it. Now, it's funny, I was reviewing the PG Partman docs a couple days ago in prep for EU to do a couple demos. And I like how Keith said it on there. And I used to work at Timescale, and we said something very similar, which is subpartitioning really can serve some specific needs. And maybe we can talk about that afterwards if people have examples. But often creating more levels of partitioning often creates more work and hassle than you think it might solve. You know, Postgres is really good at finding rows that are properly indexed, even on very large tables to, you know, hundreds of gigabytes at times. And so finding that range and where and how much you need to partition it is just something you'll learn and you'll experiment with and ask for help from others. So declarative partitioning is what I'm talking about. There's technically still two kinds of partitioning in Postgres. The other is inheritance-based. It's been around for a very long time. And it has some advantages in that you can really dictate exactly how data gets, put out to the children tables, gets distributed. But it's a lot of manual effort just to kind of keep things rolling. There are tools like PG Partman that can help with some of that. But declarative partitioning was added in Postgres 10. We added, I believe it was hash partitioning in 11. So usually I say, you know, don't really start with Postgres 11 forward if you're going to use declarative partitioning. And really it's as easy as saying, here's my table. You identify the column that contains the data that will help you partition the information into smaller tables elsewhere. And then you say, what kind of partitioning? Range, list, or hash. And we'll show you in just a minute what those are. And then the big thing here is that with Postgres's current implementation of declarative partitioning, the actual partitions where the data will reside, they must exist ahead of time before you can save data. So if you are partitioning by time, and maybe you're creating monthly partitions, if you go to insert data for October, because it's a new month, and you forgot to create the October partition for that constraint, that date range, you'll just get an error. There's no place for the data to go. So there is some maintenance in maintaining this. There are tools and other ways you can do that. Now you can create a default partition, and I'll come back around to this later. It's helpful so you don't lose data, but it's a pain when data gets in there and you later want to partition that data appropriately and so forth. So it's a blessing and a curse, but sometimes necessary depending on how you're working. And so this is a regular table, and we just have to identify in some way how we want to partition it. Now, there's a couple ways you could do a table like this if it actually needs to be partitioned. And there's some pros and cons to choosing what I'm choosing here, which maybe we can discuss at the end. But let's say I want to, I get lots and lots of payments for the system, and I do monthly reports, and I'm usually looking at the last quarter or the last year of data. And so it's easy to segment this data by date, and maybe I'll create those monthly partitions. So identify the column and get ready to partition the data. Now, if we don't use partitions, it's kind of like the buildup. Why, what's the benefit here? So if I just have that table and I know I have lots of data based on date, and I'm going to query based on a time range of some sort, if I don't partition that data, and if I don't have an index, which again, we absolutely should, but let's just pretend for a second. If we query this, we kind of hopefully know what happens. Well, the database has no way, Postgres has no way to identify rows that match that date. And so it has to scan the entire table, every page, to find and filter, to find any rows that might match. Now, if I have an index, we benefit from at least the index saying, yes, the data may be spread throughout pages on disk on a very large table throughout its storage. But I can identify the pages where rows that match your query exist. So it makes it faster and easier to get to those pages and find your data. That's great. However, what would be, in most cases in our modern world, better, particularly with things like time series data, which a lot of us have, is if we could segment that. And so not only does the query is improved by the index itself, but we have a smaller index on a smaller area, and that data gets stored inside of shared buffers. And so if I have the entire table in index, index maintenance, other things, we're going to be pulling lots of pages in and out over time that may not be frequently used or necessary, and that wastes space in shared buffers and other things. But if I can keep my most often queried data only in shared buffers, that means we have room for all the other data that we need to query alongside this. And so it's not just about compartmentalization. It is really about having an opportunity to just keep data in a kind of a contiguous space. And I don't mean physically contiguous, but pages that are shared with similar data that I know everything on that page matches this particular partition. And so there's a lot of query benefits and maintenance benefits to doing that. And some of it comes down to shared buffers and managing that well. And then the other benefit is this, is that it makes data retention or archiving really easy compared to what most of us have probably done in the past. Because it's a separate table, we can just drop the table. Otherwise, in the olden days, we had a big table that's not partitioned, and let's say we were going to delete data after a year or 7 years, whatever your financial requirements might be. And so you would run a big delete statement that is based on some predicate, some filter. Well, in Postgres, that simply marks the rows for the deletion. That's based on MVCC. And so until vacuum, which we want to see removed at some point, and everything magic for Arca, that means there's still space being taken by the data that is no longer needed. And sometimes that can create table bloat over time, if particularly vacuuming is not tuned well. It also means your indexes need to be maintained, and all of that. Those kinds of statements can create some blocking when you're doing those large statements, things like deletes like that. And so with partitions, we can simply drop them, which is a minor locking issue there. It has to just briefly detach that table from the system and delete the pages. Or we can detach a partition. That would be useful for archiving. So we might want to access the data later. We don't want to get rid of it. We just don't want it to be part of the potential query plan and being used by the system most of the time. So we can detach the partition, back it up and store it somewhere, and later either just reattach it or restore it in some way and then reattach it and so forth. So a lot of benefit, particularly as your data grows. All right, so I don't see any specific questions. Ask them out loud or in the chat. Types of partitioning. So here's the quick thing to realize, and I forgot to actually state this earlier, so I've added this. Doesn't matter what type you use, range, list, or hash. Partitioning, the table that you partition, the parent, is where you specify the column or columns that would be used to partition, segregate the data. But you define the actual ranges, values, and so forth as you add or attach the children. So the children say, I am now a partition of this table, and here is the constraint that I satisfy for those columns, right? So in a range partitioning by date, you would say, this partition is for October 1st to November 1st. And only one table can have that constraint, that you can't overlap constraints within partition tables for the partitions. So just to make sure that's clear, because I realized later sometimes it was not as clear as I was going through this. In my experience, range is probably the most used nowadays because we all have so much data and a lot of it is time series. So it's really useful for time series. It can be useful for things, maybe you just want to segregate data. If you're getting millions of rows a day, and maybe you just want to keep 100 million rows at a time in a partition because you're going to want, I don't know. So that would be like an ID, some kind of object identifier in some way. Just this many IDs, this partition, and then the next set of IDs, the next partition. And then the big thing to note here is when you use range, you cannot change this like you can a range type. A range type, you can identify inclusion on both sides. But in partitioning, it's always inclusive of the lower value and always exclusive of the upper value. What that means is this: if I'm doing it by date, It means that everything from January 1st, 0, to January 31st, 59, 59, 59, blah, blah, blah. All of those values would be in the first table, but then February 1st, 0, would be in the next partition. And with ranges, similar, right? So the first partition would store 1 to 9 values. Second one would be 10 to 19 values, and so forth. And in a range partition, this is what they look like to create. So I have a table, I identify, in this case, it's going to be payment date. So I'm partitioning by range. And then as I create partitions, I say this table is a partition of this other table. For, in this case, 4 values from, because it's a range, lower to upper values. And you just keep adding. And again, in a range, you cannot have overlapping constraints. So just have to recognize they always have to be at least, separated from one another. A list partition table is just that. It's an actual identified list of values that will be sent to a particular partition. So, it can be useful for categories of, if you sell stuff in a store, maybe it's categories, and that's helpful for some reason. Maybe it's by region or divisions within a company or within a country. An example might be if I have customers and I have billions of customers for my store. I might have in the US, I might have a state column. And so I partition by state, and I have, in this case, a Northeast partition that identifies anyone in these states will be sent to and stored in the partition for those values and only those values. And again, if something comes in that doesn't match any of your partition list values, you'll get an error unless you have that default table. And again, we'll talk about that in just a minute. And then finally, hash. So hash simply says, hey, we're going to take the value or values, the columns you give us, we're going to hash them. And then you specify essentially how many partitions you want in the end. And Postgres will do its work. And really, any type can be used in a hash partition. A date, text, numbers, numerics, integers, numerics, whatever that might be. Postgres has functions to hash essentially any data type. And so it will take those data types, create a hash, add them together if there's more than one column, and then we basically specify modulus that will be, so it helps divide it up into that many partitions. Now, why would you use hash? The reason is hash is really good when you don't have a really clear key, but you do want to segregate your data just from a management and query perspective. And so, an example might be, actually, I was playing with some stuff last night. Maybe you just have this identifier in some way and you don't really care what partition it ends up in. You just want to spread data out and do it in a somewhat, hopefully, evenly distributed fashion. So maybe you just take that ID column and you say, I'm going to hash that. And that way I know those kinds of IDs are going to end up over here, and they might be grouped with other IDs. I don't really want to manage all those tables. But hey, I want 10 partitions and hash it on this value. Now, again, you can't repartition hash partitions in the future. So if you say, I want to start with 10, there's no way to magically currently update that to say, now I want 20 partitions. You would have to create another table with 20 partitions, insert the data, delete the old data, blah, blah, blah. It is computed on the fly, David, correct. So as the data comes in, the hash is determined, and, with what you'll see next, it'll determine which partition goes into. Oh, there's a hash index for hashing part. Is there? That's a great question. Someone else might know. I don't believe the index itself is used.
Yeah, no, there's no form of partitioning creates an
That
index.
uses indexes anyway. Yeah, correct.
Yeah, the partitioning is like a level that sits in front of the indexing, right? Like if you think about range partitioning, that's sort of like putting your data in sorted order, kind of. Well, a B-tree index would put your data in sorted order, but a range partitioning scheme doesn't do that. It just breaks it up into ranges. And similarly, that hash partitioning doesn't create a hash index. It just runs the relevant columns through a hash function.
Cool. Sweet. So this is what it looks like to create a hash partition. Again, now we're just saying partition by hash. We identify the column or columns that are used for distributing that. And then, come on, why is it not? There we go. And then we create the number of tables. So I'm just showing you two. A lot of people would simply use this kind of naming structure because you're identifying the number partition. So P0, P1, so forth. Totally up to you. The names are yours to choose. And in this case, I'm saying I want 8 partitions. So I'm dividing that hash by 8. Whatever the remainder is, goes, if it's 0, it goes into this partition. If the remainder is 1, it goes into this partition, and so forth. And so you do have to have an equal number of partitions for the number that you're proposing to use, right? So if I want 8, I have to create 8 partitions with the correct modulus. So the very last one in this example would be modulus 8, remainder 7. And then it will just start partitioning that data. All right. Creating and maintaining partitions. So I showed this one earlier. I'm going to use this for the rest of my examples. Now, there are some problems with how I'm, some potential problems with the way I'm partitioning this specific table, which I'll talk about briefly at the end. But it serves as a good example. And honestly, in the demo database I use, this is one of 2 tables that has at least, multi-millions of rows to demonstrate some partitioning. And so in this case, the one thing I want to say here is, one of the other constraints with partitioning is that if you do have a primary key or unique index on the table, the partitioning column must be a part of that primary key or primary index, unique constraint or its own. And the reason is there's no global, and that would be actually, I think, 2 slides later, there's no global index. There's no global way to determine that any one value is only in this table, but not in another table, unless all of the tables themselves have the same kind of unique constraint. And so the partitioning column must be part of the unique or primary key constraint. And so in this case, this sample table previously only had a primary key on payment ID. Now, there's a lot of ways I could handle this. For demonstration purposes, I simply chose to add the timestamp because a payment ID is unique in and of itself. I could have a billion timestamps that are the same, but this is going to end up being a unique key, and we're fine. Now, do I need payment ID in this table? Probably not. I could do it other ways, but just to show you, if you have that uniqueness, that constraint in some way, the partitioning column must be part of it. You'll get an error if it's not, and so you'll be reminded. So then once I create that table, I have to create partitions. Now, I showed you briefly earlier, technically, we could create tables with the exact same schema, constraints, and everything individually, and then do a bunch of work to attach them through some other things with constraints and so forth to the parent. But that's way too much work. Instead, the best way, proper way to do this in most cases, unless you have some historical tables and data, is to simply use the create table partition of syntax. This is very similar to, if you happen to know create table like in Postgres, which will simply copy the schema of a table and other objects, indexes, and so forth if you tell it to. Create table partition of literally makes a copy of the schema of the other table, includes everything that the other table has, indexes, constraints, and so forth. And then you identify the constraints, the list values or the range values or the hash value remainder that this partition stores. All right, so in this case, I'm creating 3 by month, and the name of the partition is whatever you want it to be. Now, there's a 63 character limit on object names in Postgres, so you do have to be thoughtful about it. But most places I see will use this kind of scheme, right? Whatever the parent table name is, underscore, and then in this case, since it's date values, something identifies the range. In this case, it's the year 2024 in month 1. But again, it's up to you. You manage that. And then the other thing to mention is generally, now this is a generalized statement, most of the DDL actions you want to do on a partitioned table should be done through the partitioned table itself. So in my case, I demonstrated this is a payment to table. That's the name of this table. I'm creating different partitions, but if I want to say add a column, I have to do that through the parent itself. Even though the parent doesn't actually have any data, doesn't store anything, It is the management mechanism for many of these things. Now, there are some things you can do to individual partitions because, again, they're just normal tables. You cannot modify the schema separately. The schema of all of the related tables in a partition must be the same. And again, so that's why a lot of the things you do, you probably want to apply to all the children. And so it just makes sense to do a lot of this through the parent table. Adding indexes, for instance, you probably want the same indexes on all of your children tables because you're creating them because of your queries and so forth. So do it that way. We'll talk about one or two brief things that you can do separately a little bit later. And then some, so modifications, right? So if I want to add a column, I do it through the parent, not to the individual tables, and this will get applied to all of the tables. Now, again, if you don't, for instance, add a default value, if you add a default value that is calculated in some way, you're going to hit the same pain point you would on a big table to begin with. But this column would be added, assuming I did not, null or what have you, to the other tables. And then again, like I could create an index, right? So if I create this index, it will be applied in unique form to each individual table. Okay. And then the last thing to mention here, and this comes up a lot, and this is one of the problems with the way I've partitioned this table. And this comes up every time I give this talk, and that's why I want to talk through it briefly. This is not a global index. So let's say, for instance, maybe a better example would have been that primary key. If I have an index on the primary key payment ID, that is an index that's stored individually with each partition. That means that if I say, query where ID equals, I'm partitioning by date. But if I only query for a payment ID, Postgres doesn't know which partition it's in. And so it has to actually visit every single partition. Now, if you have an index, it should be very fast to find which partition eventually has that specific row. But there's no index that says, hey, you're not filtering based on the partition key, but you are filtering on an index I know about, and that value is stored in partition whatever. It doesn't work that way. So when you create these indexes, it is simply applying them to the partitions themselves. So I should just say, so that means you will have to mitigate that in some way. You have to decide how you partition your data. If that's something you are always going to need to do, you query by date, and it makes sense to really partition it by date. But you also need to go update individual, ID values over and over. There's going to be a little bit of a conflict there, and you have to decide which way to partition it that makes sense. And so there's a couple ways you could do that. And then as far as retention goes, we can drop it's just a table. So if you want to get rid of a partition, you just drop it. If you want to detach a partition, you can do that. And then again, you can reattach or attach. Yes, you can range partition without a tree index too. Absolutely. So there's a lot of good conversation going on inside. Robert's a master at just about everything Postgres. So, and there's other folks on here that are as well. So please keep going. The attaching a partition. Now, in this case, I detached a partition and then I reattached it. It's easy because it already had the same schema. It already has the same constraints. However, if it doesn't, then you won't be able to attach it. So you can attach tables later. If you have old data or you import older data, you can do that into a table, kind of clean it up if you want, and then simply attach that table as long as the schema matches. And then any indexes you've created on the parent will then be added to the table when you attach it if they're not there, and some other stuff. All right. So that's data retention and maintenance. And last but not least, the default partition. I've mentioned this a few times. So when declarative partitioning came along, man, you guys are going out of here. This is good stuff. I love it. The default partition is kind of a necessary evil, is what I say, or necessary help. In many cases, if you ever have the thought or you have experienced in the past, data comes in unexpectedly that may not match a particular range. Well, since declarative partitioning will not create the partition for you, it has to exist. If you ever run into that, and you just want to fail safe, you can create this default partition. And essentially, the default partition ends up having a constraint that is not equal to the other constraints. And so anything that comes in that does not equal the others will match a constraint outside of all those ranges or lists or what have you for that one partition. And at least you can save the data. The problem is if you want to move that, you realize, oh man, there's data in there, and you want to actually put it in a correct partition and get the value, then you have to do exactly what I just said. You first have to create a table, copy the data out with the correct constraints, and then you have to remove the data from the default partition so that there's nothing in there that matches that same constraint. And then you can attach the partition with the new constraint with the data. And it's a headache, honestly. That might get easier in the future. Maybe there'll be ways to deal with that. But right now, it's a great way to prevent data loss and not having to worry about that. But it can be a maintenance headache over time. Just recognize that. Now, how do you do that? You just literally say default. This works for all three, doesn't really matter. And most people, again, just do like underscore default as your naming scheme or something like that. So up to you, you get to name it and we'll go from there. Keith, the other problem with the default is every time a new child is added, yes, you're right. It has to scan all the data in this file. Yeah, great point. And that's kind of goes back to the constraints because it doesn't, if there's data in there and you have it, it has to first make sure before I can attach this new, even this empty table with these constraints, that there's no data in there that matches this constraint, or I can't attach this partition yet. And you have to go through the rigmarole that I just briefly talked about, creating a table, blah, 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 and so forth. All right. And then partition automation. I'm working on a couple slides. Maybe I'll get back with Keith after the fact. PG Partman is, so I would say two things. Do not plan, if this is really where you're going to head, if you really have a table that should be partitioned, do not plan on your partitioning being a manual process. It's going to fail at some point. It doesn't matter how many you create in the future, in the past, whatever. It will likely fail at some point. Someone is going to forget. That person's going to leave. It's going to get lost in a, some kind of, checklist you normally have. And so do something more automatic. And there's lots of ways you can do this. You can use a tool like pgcron and create your own script that runs on or PG timetable, any of those, that runs a script every so often and make sure there's enough partitions when you have something like range in the future, in the past, what have you. You can use a tool like PG Partman. It's available. Both of these extensions are available on every hosted platform I know of. And so they are just easy tools to get started with. PG Partman will help you with range and list partitions and keep things moving in various ways. And there's a lot of functionality there. So when you start a partition table, it will allow you to say how many partitions it should create automatically right then. And then you can schedule it either through pgcron or through its own background worker to run every so often and just ensure that there's enough in the future so you don't run into that problem and so forth. So check those out. Some great options there if you just don't want to do it yourself in some other way. There are other extensions that actually do help with creation of partitions. So timescale DB is not declarative partitioning. If you're doing time series data, not just because I used to work there, I do still think it can solve some really interesting needs. But it's just partitioning at the end. But because of how they created the extension years ago, it will actually create partitions for you, time partitions, if they don't exist to match your specific scheme. So that might be useful. Citus, same thing. It actually has functions that will help you create partitions, at least a chunk at a time. I don't think yet it has something to do automatically. It has been a while since I've looked, so that might have changed. And then I didn't know this until recently. I was working with a customer of ours who's using EDB, a distributed server, and we were talking about partitioning. They were having some problems, and I was really confused, like, well, how are you doing this? And I did not know that advanced server with distributed server actually has some functions for automatically creating partitions as well. I haven't used it. I just realized and learned that it's there. So there are various Postgres variants that will help you do some of this as well. But if you're using Postgres vanilla, you're doing declarative partitioning, either do some kind of script on your own so that you're assured of that, or check out something like PG Partman to help. Now, I'm going to skip to the other part. If we have time or you guys feel like you want a 8-minute demo, I can do it. But let's just skip to tips and tricks because I feel like some of this is valuable as you're getting started looking at partitioning. So merging and splitting partitions. I said that at the very beginning as something I would add. It's not currently possible. There's no command that says, oops, I meant to make, or I have lots of old data and I'm doing daily or weekly partitions. I just want to combine them into monthly because over time, it's just easier to manage and it just makes my life easier. There's no way to do that automatically. Again, you would have to create a table first, copy all the data in with the correct constraints, drop all the other partitions, and then reattach the new one with all the data. Now, there was a patch in Postgres 17 that was being talked about. I think there was some testing done on it. In fact, I think I could be wrong, but Robert might have been the one, and I think he's just now left. It was close, but there was a couple problems found with it, so that patch was backed out. But there is discussion on getting that back into Postgres 18. So it might come around. We might have some functionality for that. Like I said, you can accomplish this yourself. It just takes a little bit of effort. This is probably the most common question, aside from what columns should I use to partition? And there's a whole lot of ways we could talk that through and get some feedback from others. People have done this for a long time, so there's probably some good community support for exactly how to do that well. By and large, the main things are still the main things, right? We get to specify shared buffers, the amount of space that data pages that are in active querying or manipulation are stored in memory. Now, the going rate, even to this day, is like, hey, start at 25%. You certainly can go bigger than that. I've seen things like upwards of 40% for certain kind of workloads. That's one discussion, but the reality is, if you have really, really big tables and they literally just can't fit in shared buffers or nothing would be able to fit, keeping the most recent data, the data that's being queried most frequently, if that is of a size that can sit in shared buffers alongside all the other stuff, that's just a way to think it through. Think about how much memory you have for shared buffers, think about all the data, and then think about like, okay, the hot partitions, I want that to take X percent of, my memory in some way, shared buffers. I just kind of had that mental model. That's one way to think about size. The other thing to think about, though, is too many partitions can cause problems. And it just means that planning will take longer. It does mean some other maintenance things just have to scan more more tables. Um, there's some lock issues. I had not thought about this before because I just never had the specific query pattern. There's an article. I need to go find the link. I thought I had included it and then I realized I lost it. So I have to find it. It was one of the companies that was talking about using Postgres, and I forget exactly who it was. And they ran into a problem with Postgres 13 below. There used to be an issue with some lightweight locking problems. There's only so many lightweight locks that can be taken at a time. And they happen to have a really large table that they had partitioned, I think, by day for their specific pattern. And then eventually they did something else with it. But and they had like 20 some indexes per table. And so every time you run a query, depending what happens, there instantly becomes a lightweight lock on the table and the indexes and maybe some other stuff. And there's only so many. And so they were running into this issue where queries were being blocked because they were waiting for the availability to use lightweight locks. And so that was just a new thing for me to learn. I just like, oh, I hadn't considered that math. 20 indexes per partition. You start to get 10, 20, 30 partitions, and all of a sudden you're talking hundreds and hundreds of locks. Theirs was larger than that. It's just something to think about. And then I would just say, absolutely make sure that your partitions have relevant indexes. And what I say here is, this is one of the things that you can do to a partition itself. You can add indexes to individual partitions that are not a part of the actual partition table definition. This might be really helpful if you happen to know that you have a partition that stores some data that maybe isn't completely balanced. You can create a specific partition for a column. Maybe it's your hot partition and you just want something really specific to be able to be queried. You can add indexes to individual partitions. I would just say this as a last deal. There's one more slide here then. Partition size, don't try and base it on number of rows because that's kind of arbitrary. And, the width of the row matters and the size. And think about your data and what actually makes sense. If it's a list, how small do you want to make the list? If it's range, what makes sense? Am I getting, I can get 50, 100 gigabytes per partition and still probably query pretty efficiently in many cases. So just think about that. And then alongside it is data retention. If you're doing date-based stuff, do you want to drop data every month after 2 years? Well, then you probably want monthly partitions at the bare, at the most, depending on your patterns. So, and then 2 quick things. Hopefully this makes sense. Always query. If you're going to partition a table, you should make sure your queries always include the partitioning key. If they don't, Postgres has no idea how to go find that specific row of data that you think you're trying to access. If the partition key isn't included, it will have to scan every partition. And if you're subpartitioning, it will have to go through every subpartition, right? So it just keeps the problem will grow. So if your query pattern doesn't support it, then you got to figure out a way for the query pattern to support it. Maybe it means you have to do some kind of composite column that becomes your partitioning column or something like that. Think that through. Could just be really valuable and beneficial. For dates, before Postgres, I always forget, and I keep forgetting to spin up an older container to check. I think it's 15. It might be 14. The now function is a volatile function. So when you're doing date ranges, for instance, if you happen to make a query like the second one, now minus something, in older versions of Postgres, now is a volatile function. And so it couldn't identify in query planning time how to prune the partitions it's going to scan. Now at execution time, it would be able to evaluate it and then do it. But the planning time would be increased because it assumes, well, I don't know exactly what that date is. So I'm probably gonna have to scan every table, every partition. That's been improved. But if you can, identify that date and actually insert it into the query ahead of time, that just kind of, gets rid of, if you're using a ORM or, whatever your framework is when you're creating the queries in your app, if you can inject the actual literal date first before it's executed, you kind of overcome that whole thing. And last but not least, they're tables. So they can be, they can have their own schema. There's some good reasons potentially for doing this just organizationally. The partitions can be in a different physical namespace than the parent partition. Again, you're attaching it to that partition. Now, why would you do this? It might be that you have a couple different partition schemas for your partitions. One is your slow memory for really old data, your slow disk. So this becomes something like data tiering. You can move partitions to other schemas that have other table spaces, or sometimes it's just for organization. You're going to query through the parent table anyway. You don't really care what the namespace of the other ones are generally. It can just clean up just the visual side of managing the database. And that is essentially it. This is just an example of actually altering the table space on a partition table, a partition itself, and then the index. If you move a table, the indexes don't move with it automatically, so you do have to do that as well. And that is a whirlwind tour in about 35 minutes of all the big basics of partitioning. And there's a lot more to talk about. But please, ask whatever questions you have. I was going to briefly pull this up just to show you, I do look every release. I will say this, since partitioning was added, there's always some new stuff being done to it. So check the release notes to see what's been happening there. I think there's 6 or 7 things added in this specific version. Like I said, we might get like the merge and split apart functionality. So check out the next release to see if that's been included.